This is a wall that stretches for more than 13,000 miles, across deserts, over rivers, and along knife-edge ridgelines. Built without steel cranes, bulldozers, or GPS, it's been nicknamed the longest cemetery on Earth. But the secret behind the Great Wall of China isn't brute force. It's an engineering system that adapted to every terrain it touched, scaled logistics across a continent, and kept evolving for 2,000 years. When most people picture the Great Wall, they see a single stone dragon snaking through misty mountains. The reality is bigger and smarter. What we call the Great Wall is a network of walls, beacon and watchtowers, gates and passes, garrison towns, and supply depots built and rebuilt by different states and dynasties. A national survey in the 2010s totaled roughly 21,000 kilometers, about 13,000 miles, when you count walls, trenches, and natural barriers designed into the system. The famous masonry near Beijing is predominantly Ming dynasty work, and the Ming line alone runs roughly 8,850 kilometers, about 5,500 miles. Numbers vary by what is measured, but the engineering principles stay consistent. Use the landscape, standardize what you can, and keep your supply lines breathing. The earliest chapters weren't grand blueprints, they were emergency lines. During the Warring States period in the 7th to 3rd centuries BCE, rival kingdoms raised local barriers where steppe cavalry could strike. Their go-to method was rammed earth, hangtu. Carpenters set up stout timber frames. Crews tipped in thin lifts of loess and local soil. Men with heavy wooden tampers compacted each layer until it rang like stone. For strength and drainage, builders mixed in pebbles, gravel, reeds, and tamarisk twigs. The result wasn't pretty, but it was fast, economical, and surprisingly durable in dry climates. In deserts, engineers laminated reed mats with sand and pebble courses to make composite berms that resisted wind scour and salt attack. In mountains, they anchored low earthen ramparts onto ridgelines that multiplied height for free. These lines weren't continuous from sea to desert. They were cords thrown across choke points, often parallel or staggered to trap fast horsemen in kill zones. In 221 BCE, Qin Shi Huang unified the states, and suddenly a patchwork became a policy. The first emperor ordered existing walls linked and extended to blunt raids from the northern grasslands. Organization mattered as much as materials. Surveyors walked ridges and river crossings, marking routes that used cliffs, saddles, and ravines to best effect. Corvée labor, conscripted citizens, and troops moved in seasonal waves. Freezing winters set tamped earth hard. Spring and autumn opened mountain passes for hauling timber and stone. Teams worked like a traveling factory. Carpenters leapfrogged shuddering forward, haulers cycled baskets of fill, tampers marched in rhythm, supervisors scratched quick marks on fresh courses to track output. Watchtowers rose as nodes, stone-capped earthen cores where smoke by day and fire by night could signal across the horizon. From the start, the wall was more than a line. It was an information network. Later, dynasties rebuilt, shifted, and extended the frontier. The Han pushed west along the Hexi corridor, tying walls to oases and way stations that protected trade and taxation. Soldier farmers, the Tuntian, planted grain near garrisons to cut transport costs. Warehouses at gates stored millet, salt, and tea. Armories held crossbows, bolts, and armor. Cisterns captured snowmelt because water is logistics. Failure modes taught hard lessons. When drainage was ignored, rain soaked earth cores, froze in winter, and burst walls from within. Builders learned to carve weep holes at the base of parapets and along the wall body to bleed storm water. They learned to cap earthen crowns with stone coping so meltwater shed cleanly. Where slopes slumped, they added buttressing, short retaining wings that pushed back against gravity. The biggest leap came much later. When the Ming seized power in 1368, warfare had changed. Siege artillery and organized enemy cavalry demanded stronger, higher, more standardized defenses. The Ming rebuilt vast stretches in brick and stone. Foundations were keyed into bedrock with big granite blocks. Curtains rose in fired gray bricks bound with lime mortar. Interiors packed rubble and small stone to save material. Crenellations, alternating merlons and crenels, crowned the parapets so archers and later gunners could shoot from cover and step behind solid blocks to reload. Steps and ramps followed a modular rhythm so troops could move quickly along the crest, which doubled as a paved highway. Drainage culverts under the walkway and scuppers cut into the parapet released trapped water so the wall wouldn't tear itself apart in storms. In some Ming fortifications, including sections along frontier lines, lime mortar was blended with sticky rice porridge. The amylopectin in the rice improved adhesion and water resistance, helping joints stay tight centuries later. Industry underpinned every course. Brick kilns sprouted near clay beds fired by carefully managed forests. Simple clamp kilns turned out millions of standardized bricks, many stamped with the workshop or battalion that fired them, marks archaeologists use to date segments today. Quarries near passes cut coping stones, stair treads, and quoins. Ox carts and wheelbarrows moved loads on flats, while sledges, shoulder poles, and sheer human chains took over where wheels failed. In winter, crews sometimes poured water on sled runs to freeze slick chutes, sliding heavy blocks upward with lever bars and rope teams. The point wasn't to fight the mountain, it was to turn the mountain into a machine. Just as important, the Ming made the wall explicitly nodal. It's easy to see a long line on a map, but the real power sat in the knots. Fortified mountain passes like Shanhai Pass, where the line met the sea, and Jiayuguan, anchoring the extreme northwest. Garrison towns tied to the weisuo system, a grid of military districts that rotated soldiers and responsibilities. Logistics depots with granaries, fodder sheds, and horse corrals. Move to a tower and you see command built into masonry. Beacon towers kept line of sight to neighbors. By day, smoke sent coded counts. By night, stacked flame signals did the same. Drums and horns covered foggy mornings. Riders relayed confirmation along the crest road. In good weather, an alert could ripple hundreds of miles in hours, long before an enemy column reached a major gate. The wall you walk on was also a message bus. Materials and methods shifted with geology like a language changing its accent. On the Loess Plateau, Hang-Tu stayed king because Loess compacts into brick-hard lifts and resists dry erosion. In high granite ranges, stone footings grabbed bedrock, and brickwork rose because bricks pack strength per kilogram and stack neatly in bundles for hauling. In deserts, where salt attack and wind scour kill both mortar and pride, the answer stayed low and flexible. Reed earth composites, stamped berms, and frequent beacon stations instead of ambitious high curtains. River crossings were never afterthoughts. Walls dove to meet cliffs or ended in forts that controlled ferries and bridges, because a frontier is only as strong as its gates. Where the line walked the edge of sheer ridges, terrain provided a 1,000-foot drop on the enemy side. On the interior side, gentle steps let garrisons move fast without exhaustion. Archaeology lets us read these solutions like blueprints. Brick stamps record workshops and dates. Lime mortar chemistry reveals recipes and water sources. Tool marks on quarried stone show chisels and wedges rather than explosive splits. Beacon towers preserve ash layers from repeated signaling. Paleo-environmental cores track dune migration and river shifts that forced new alignments. In places, abandoned branches tell a second story. When politics moved frontiers, maintenance stopped. Without coping stones, rain eats into cores. Frost heaves splits merlons. A missing weep hole balloons a wall after one wet winter. The ruins are case studies in deferred maintenance. A few myths need pruning. Bodies weren't mixed into mortar. While the death toll in certain campaigns was real, the dead were buried near the works, not between bricks. You can't see the wall with the naked eye from space. It's too narrow and earth-colored, and there is no single unbroken ribbon from sea to desert. Instead, there are parallel lines, spurs, and branches that create depth, funnel movement, and force choices on invaders. That S why the wall looks like a road system in plan, it S about options, not absolutes. Manpower and seasons mattered as much as stone. Early states relied on corvée, mandatory service, then mixed in hired craftsmen. Soldier farmers in Tuntian systems fed themselves and the forts. The Ming weisuo rotated garrisons across districts to limit local collusion and keep skills fresh. Building campaigns breathed with the calendar, quarrying and felling in autumn, heavy hauling in winter when frozen ground carried weight, brick firing and high work in spring, mortar finishing in dry early summer, monsoon season reserved for repairs and clearing drains. Even a great project has to move with weather. So why move from earth to brick and stone? Gunpowder is a big part of the answer. Artillery and better siege tools made soft ramparts vulnerable. Brick offers compressive strength and regularity. Stone footings resist undercutting. Lime mortars, especially where blended with sticky rice, lock units together and shrug off water better than packed soil. Standardization meant quality control. Bricks from one kiln matched those from another. Stair risers repeated. Parapet bays repeated every few meters so crews could build by muscle memory. Standard parts, speed training, building, and repair. Stand on a preserved Ming ridge, and the details read like a field manual. Merlins, the solid tooth blocks, give shoulder-width cover. Crenels, the gaps, are splayed for a wider field of fire. Loopholes below serve crossbows. Drain scuppers notch the inner parapet to shed water off the walkway. Retaining revetments brace fill against the mountain's fall line. Stone flumes dive under the path so storm water can cross the wall without tearing the core. Small bastions puff out at intervals so defenders can sweep the face with enfilading fire. The top is a road, the side is a cliff, and the inside is a storehouse of choices a commander can make at speed. If the Great Wall has one unifying idea, it's that geography is free engineering if you know how to spend it. A cliff is 1,000 feet of masonry you don't need to build. A saddle between ridges is a natural gate that focuses trade and tax. A cold, dry winter is a cement mixer if you time-rammed earth to freeze set. A reed bed in a desert is rebar when you layer it right. The wall is therefore less a structure than a system. Terrain, materials, labor, season, signaling, and logistics woven into a frontier instrument that worked even when parts of it crumbled. From the rammed earth ramparts of the Qin to the brick and stone fortresses of the Ming, the Great Wall stands as one of humanity's clearest proofs that engineering, organization, and landscape intelligence can scale farther than any single monument. It isn't just a barrier, it's a 13,000-mile operating system. Enjoyed this evidence first dive? Like the video and subscribe to Unfolding Legacy for more history decoded.